Hello viewers, this is the video lecture for the topic Describing Semantics. This is from the first unit of Principles of Programming Languages. Describing semantics. Semantics refer to the meaning associated with the statement in a programming language. It is all about the meaning of the statement which interprets the program easily. There is no single widely acceptable notation or formalism for describing semantics. Several needs for a methodology and notation for semantics. Programmers need to know what statements mean. Compiler writers must know exactly what language constructs do. Correctness proofs would be possible. Compiler generators would be possible. Designers could detect ambiguities and inconsistencies. So, there is a need of understanding the semantics in a programming languages. There are three types of semantics: operational semantics, denotational semantics, axiomatic semantics. Operational semantics. It describes the meaning of a program by executing its statements on a machine, either simulated or actual. The change in the statement of the machine defines the meaning of the statement. To use the operational semantics for a high level language, a virtual machine is needed. A hardware pure interpreter would be too expensive. A software pure interpreter also has some problems. The detailed characteristics of particular computer would make actions difficult to understand. Such a semantic definition would be machine independent. A complete computer simulation can be used to understand the semantics of a programming language. It build a simulator for the idealized computer. Use of operational semantics, language manuals and textbooks can be generated. It is used to teach the programming languages. There are two different levels of uses of operational semantics: natural operational semantics, structural operational semantics. Denotational semantics. Based on the recursive function theory, it is the most abstract semantics description method. It defines a mathematical object for each language entity. Define a function that maps instances of the language entities onto instances of the corresponding mathematical objects. The meaning of language constructs are defined by only the value of programming variables. Denotational semantics. Program state. A state of the program is the values of all its current variables, such as s equal to I1, V1, I2, V2 up to In, Vn. Let var map be a function that when given a variable name and state, it returns the current value of the variable. For example, var map of ij, s equal to vj. Evaluation. It can be used to prove the correctness of the program. It provides the rigorous way to think about programs. It can be an aid to language design. It has been used in compiler generation systems. Because of its complexity, it is of little use to language users. Axiomatic semantics. It is based on formal language, that is predicate calculus. It is used for formal program verification. Axioms or inference rules are defined for each statement type in the language. The logical expressions are called assertions. An assertion before a statement states the relationship and constraints among variables that are true at that point in execution. An assertion following a statement is a post condition. A weakest precondition is the least restrictive precondition that will guarantee the post condition. Example: a equal to b plus 1, a greater than 1. Program proof process. The post condition for the whole program is the desired result. Work back through the program to the first statement. If the precondition on the first statement is the same as the program specification, the program is correct. An axiom for this: assignment statements. So this is the example of inference rules. Inference rules consist of the sequences and the substitution. And in the previous example, there are some characteristics. Characteristics of loop invariant having the following conditions: P equal to I. An evaluation of Boolean must not change the validity of I. The loop variant must be true initially. I is not changed by executing the body of the loop. If I is true and B is false, Q is implied. So these are the conditions. The loop terminates. The loop invariant I is a weakened version of the loop post condition, and it is also the precondition. I must be weak enough to satisfy prior to the beginning of the loop, but when combined with the loop exit condition, it must be strong enough to force the truth of the post condition. Evaluation of axiomatic semantics. It is somewhat difficult, but it is good tool for correctness proof and an excellent framework for reasoning about programs. In operational semantics, the state changes are defined by coded algorithms, but in denotational semantics, that state changes are defined by rigorous mathematical functions. So that's all about the topic. Thank you.